And so these PUFs, how it comes from the process variation when you manufacture a chip. And there's various implementations, so I will go through it later on, but I'll show you some examples here already. So you can have SRAMs, you can have also ring oscillators, and you can have some delay elements which can be used to have PUF property on a chip. And it's this with these circuits, we can generate some digital ID out of the PUF. And this digital ID can be later on used for key generations, entity authentication, anti-counterfeiting, and some IP protection applications, and I will go through them later. So first, let's see how the variability comes into these digital circuits, these CMOS circuit, these ICs. So it's inherently presented in all the ICs. So there's variability in transistors, and there's variability in the interconnect of these transistors. And in general, they are undesired for most of the circuits, but not for PUF. And the variations can come from the random dopant fluctuation, as you show here the cross section of a transistor. And you cannot make it always a desired dopant as you like. And for the interconnects, you do not always have the same width of your interconnect, so it can have a variability of it. So why the PUF is now within our interest? Because as the technology scales, we have actually more variability that we can explore. So when you talk to the semiconductor people, they always talk about Moore's law, and what Moore's law is basically it's the dimension of the transistor. It shrinks by a certain scale in a certain time. And for example, it's now the technologies has moved from already to 7 nanometer and even beyond. And how's the effect of these new technologies and with scalings? It's introduced more variabilities from you need more processing steps to in this technology. And if you decrease the size of the transistor, for example, if you have a fixed variation of 2 nanometer, it's 5% in a 40 nanometer technology, but then it will become 30% difference in the 7 nanometer technology, basically. And of course, if you want to manufacture new devices, you also need to use new materials. Then it's also introduced more variability. And as you see, here's some example from the transistors. They are moving from the old technologies, more planar devices. And as the transistor evolves, then in the newer technology, you have FinFET, and it's more like 2.5D already. And then you also have the 3D structure as the gate all around the transistors. It's an example. So in this the new devices, we can already expect more variability that can be used in our PUF designs. So let's briefly introduce how the variability comes from, and then I'll go to the next topic. Is about some basic implementations of the PUFs. So in PUFs, we have two main design methodologies. One is here shows illustration. So for example, we have on the chip, we have some elements with variations. And in this case, we extract from each element, we extract some bits. We call it a response. And in this case, we have 9 elements. Then we have 9 response corresponding to these elements. And this method, we call it a weak PUF. And why we call it a weak PUF? Because if you see the number of elements versus the number of outcomes, it's actually linear scales with the number of elements. And the next one is so we also have some blocks with process variation. But in this case, we don't read out them individually, but we've put them into a magic box. And in this magic box, we give this an input. We call it challenge. And in this case, it will produce a response corresponding to all these variations and also to the input. And in this case, we call it strong PUF because in this case, the number of elements, the number of outcomes will be exponentially scaled with the number of elements because we can have a lot of inputs, and this inputs actually is corresponding to the number of elements. So we can, this one will show clear in the later on examples. And so why we need these two different type of PUFs? So let's see a first use case of the PUF. So actually, we want to use it as a replacement of the non-volatile memory to store the secret key. So in the typical case, you would in the device you need to do cryptography. You need to store the secret key somewhere, and typically it's stored in the non-volatile memory. It can be a ROM, it can be a flash memory, it can be fuses, it can be also battery-backed SRAMs. But what's the issue with this solution? It's have some concerns that some people make some physical attacks on these non-volatile memories. And also another important aspect is that these memories on the chip is actually more expensive than the transistors itself, so it's more cost. So you don't want, sometimes you don't want, for IoT devices, you don't want this high cost memory on your chip, basically. So we can then use a PUF to, as we mentioned, it can generate its own unique response. So we can use a PUF to generate the secret key, a unique secret key of a chip. So how is it done? Let's show a classic example of an SRAM. So typically in an SRAM, you have a two-dimensional array of these 1-bit memory elements. So this SRAM is like a conventional one used a lot in all the technologies. So where is the variability? It's the mismatch between these two identical manufactured inverters. So as you see there, the left transistor, there's an inverter at the left and an inverter at the right. And if you plot it in a more simplified block diagram, you'd have an inverter, two inverter connect back to back, and it forms a loop. And in this case, for SRAMs, you can the circuit state can be stable either for have the uppercase or the lowercase. And how we use it as a PUF, so let's assume we don't have a data stored in the SRAM when we power it off. But when we power it on, it would we don't provide it a data to store it, and then it will automatically select which data it appears because it needs to be stable. So that's how basically it's used as a PUF, and I will show the example how it really works later. And there's another property of the SRAMs because it's volatile, so the data would gone after you power it off, and in some cases it provides more security if it's lose this data when it's powered off. And so how we get from the transistor variation to PUF bits. So again, let's see the SRAM, and we make an assumption that one of the key 4 transistors, one of them is much weaker than the others. So we just assume it's already not functioning. And for this case, you see there's no path to the ground. In this case, it's left. So the left node would definitely be a 1. And so the right would be a 0. So it's a definite case. And we see another extreme case as well. It's in terms it would be another state. And if we assume the other transistor is broken, then we can know for what's the effect we get from if we have a weak transistor in these devices. So yeah, we show the 4 extreme cases. So this is like the case that we want it to happen, but actually it's not always happens as we desired. So it's always like a mix of these cases. So what if we consider another extreme case which we don't have any variation in the in this particular cell? So if we assume that the 2 PMOS transistor and the 2 NMOS transistor are completely identical, and in this case we don't know it preferred a 0 at the left or a 1 at the left. So in this case, once we power it up, it would basically determined by noise. So we then don't have really a PUF. We have more like a RNG in this case. And also another non-ideal effect is that if the variation throughout the chip is not actually uniform, it's not completely random. So in this case, it may result in a good case at the left, it seems to be random, but the right case, you can see that in this example, it shows some obvious pattern that you can see that it's not as random as the left one. So these are the 2 non-ideal effects you can find in the PUF. And so how we deal with these non-ideal effects. That's we see how we make it from a process variation, which is not so ideal, to a secret key that we can actually use. So let's assume we want to generate a 128-bit AES key in this case, and we have a PUF, and we read out the value of a PUF. We have m bits of PUF response, but we cannot directly use it because it's noisy. So how we later on we have to feed it to we call a one-time enrollment step, which is done basically off chip. And it's take the first measurement, we call this, we take this first m bit as the golden data, and we feed them into this so-called helper data algorithm, and it will generate the key that we actually want it to have, and we will store it in the server. And in the meantime, the helper data algorithm will generate helper data, and the helper data is stored in the non-volatile memory on the chip, which is later on being used to do error correction, to reduce noise, and to do entropy extraction to make the output key to have high entropy, and it can be secured to use. And so this part we call the post-processing, and it's typically needed in most of the weak path applications. So later, after we discuss about this first application, then we take another example on showing how strong path is used. And then so here the strong path is proposed because we want to use it to realize kind of an ideal authentication scheme, which is fully based on the challenge and response behavior. So let's assume we have some paths which give us acting as a strong path, and if we apply a challenge, it would give a corresponding response. And so the first step is for the server, it will generate some random challenges, a lot of challenges to these paths, and it will collect back all the response corresponding to these challenges and stored in the database. And when this server, it wants to authenticate one particular device, it would send a recorded challenge to this device. And this device would generate the response based on this challenge. And the server would determine if this device is the device that I know based on if the response is the same as the one it's stored in his database, basically. So so that there can be an enrollment and authentication based on these strong paths. And so what is needed is that you really need a huge amount of challenge and response pair which are uncorrelated. Then you can basically you can really use these schemes. But yeah, typically it's not that ideal. So I will show the example later how things can go wrong. And so this here shows the most classical example for a strong path. It's called Arbiter Path. It's based on the timing differences in the circuit. So as you see here are a lot of elements which are, the function is you can select these elements to let the signal go through directly if it's a 1, or you select it as 0 and it will go across by each other. And how this works is that so this one is called a challenge. So based on this challenge, you will get a different configuration of these circuits, and then you will result in a different timing difference. And this timing difference is determined by this arbiter circuit. So if the upper one is faster, it will become a 1, and if the lower one is faster, it will give a 0, basically. So yeah, in this case, if you have m bits of challenges, you can have 2 to the power n challenges combinations. Also, you have 2 to the power n challenge response pairs. And these element is actually implemented by 2 multiplexers, and the arbiter is basically implemented by using the SRAM latch. And I will show the operating principle and and show how it is not actually an ideal strong path. So assume we have a signal comes in, and we have the signal with the certain timing difference based on the input. And these inputs are actually linearly additive by sum up of these the delays of each element. And you see here we have different delays for each element based on the 1 or 0, and it's randomly because it's random, comes from the random process variation, so we don't know how the exact value is. But assume that we want, because we want the challenge response to be uncorrelated. So let's assume one correlated case, which we only change 1 bit from the challenge. And in this case, only this challenge would change. Only these only one delay would be different. And if we only change this difference, and the outcome of this delta t would be only a bit different from the previous one, and because the first number is a sum of n elements, and later on is only from 1 element, so it's actually the distribution of the first one is more spread than the second one, so it means it's less likely to change the outcome if we only change 1 bit. So basically, if you change only 1 bit, the outcome of this strong path would be more likely to be the same as if you don't, it's the original one. So basically, in this case, we know that in these implementations, the challenge and response pairs are not actually uncorrelated. So it cannot be an ideal strong path. So in practice, how people evaluate can we use this as a strong path is to do some attacks. So in this case, because there's highly correlated, so they are prone to machine learning attacks. So here shows an example. If you do in this paper, if they did some trainings on the challenge response pairs, and it only need like thousands of challenge response pairs, it would be able to model this path with high accuracy. So basically, in this case, we cannot really use it as to implement the ideal authentication scheme that we desired. So so there are also some methods to deal with these non-ideal effects. So it can be somehow improved by XORing the outcome of several strong arbiter paths in one. And so the XOR operation is actually nonlinear, so it makes the challenge response less correlated, and it will need more challenge response pair to be able to train the model, basically. And so assume we have 1 bit flip in the challenge, it resulting in 5% of the flip of response bits. Then if we XOR it by 3, it makes this probability to become 14%, which is higher than the 5%. And so it will be more resilient to machine learning attacks. But then the question comes, can we just infinitely increase the number of XORs, then we make the machine learning attacks not feasible? And the answer is no, because the number of XOR we can put there is limited by noise. So because the XOR operation will result in noise amplification. So assume we have some input with different bit error rates of like 6%, 8%. But if we XOR them together, you can simply compute what's the outcome, the resulting bit error rate. It will become higher, it will become 16%. So if soon we have even more XOR, we will basically get almost to the 50% of bit error rate. So it basically adds like also acting like an RNG in the end. So now it makes still an ongoing, there's no answer on this question. So in the path research field, we are still looking if there's any possibility to make really an ideal strong path. But till now, it's no clear solution. So later on, I will not mentioning strong path. I will be more focusing on weak path in my later presentations. So as we talk about these two basic implementations, then I will show you some basic path properties. And basically, it's more focusing on the uniqueness and the reliability of the paths. So first, about uniqueness. So what is uniqueness? So basically we want it to be acting like a chip fingerprint. So of course we don't want two chips to have the same fingerprint. So basically for the path response of this left chip and the right chip, they should be different. So this R1 shouldn't be equal to R2, and it needs to have a certain difference. Then you cannot predict one by another. So how we estimate the uniqueness in this field, we also usually use the Hamming distance of the two responses, which you can calculate it. So for R1 and R2, so you see the underlined of the R2 are the bits which are different to R1. And if you give each difference a 1, and you sum up these ones, it shows the Hamming distance of these R1 between R1 and R2. So what's that? So if you have a lot of paths and then you calculate the Hamming distance of all of them, it will give you a case like a binomial distribution. And here shows an example. This example is of our design, and it's actually the blue one is the measured Hamming distance, and the black curve is the ideal binomial distribution. So they should be really close to each other. Okay. But here shows, but if we want to do, as I said in weak path, we want to use it to generate a secret key. And for generate a secret key, you need to know the entropy of it. So how we understand how can we make from the Hamming distance to entropy, we need to estimate actually how much entropy it has, right? So for a key generator, we need to know also the mean entropy, as Vladimir just mentioned. So here shows here's the reminder for how it's defined, and basically it shows how these secret variable can be predicted, and it's more conservative than Shannon entropy that we typically use. And just an example, if you have these uniform distribution, you have more entropy comparing to this ununiform distribution. And in the secret key that we desired, it needs to be, for example, 128 bits. It need to have full entropy. You need to have exactly 128 bits of mean entropy. And so it needs to be uniform distributed. And resulting, you have the minimum probability of guessing this key correctly in the first time. So as is said here. So, but yeah, we care about the mean entropy of a path. So the problem is here shows how the calculation of showing how you cannot really exhaustively estimate the path entropy because you have to implement so enormous amount of paths in order to really do the statistic to prove how much mean entropy you have. So typically you can only do some estimation by the minimum, by some limited number of outcomes. So for example, you can estimate the mean entropy by looking at how the data, actually the resulting data of a single path. It's not really a precise estimation, but you can know the mean entropy of the left one should be higher than the mean entropy of the right one. Okay. So typically in real case it's more complicated. You have to feed these measurement data, limited amount of measurement data to a mathematical model, and then you can kind of have a good estimation of the mean entropy. But the procedure I will not mention it here because it's too complicated. And so again, how we from the path to a secret key, as we mentioned previously, you have resulting from n bits to 128 bits of secret key. So it's basically from the starting we have a path with not full entropy, but we can, based on the Herbert data algorithm, we do error correction and we do entropy extraction. We finally have a key which is uniform and stable with full entropy. And this we know that's this scheme would only work if you have already the mean entropy higher than the 128 bits. So for example, you don't have enough entropy in the first place, then this scheme will not work. Okay. So then, yeah, basically this is the first property that we want the path to have. It need to be unique, and later on it need to be, again, for all the circuit, it need to be reliable as well as path. So the first, we want to check how reliability affect path, because you want to, as we mentioned, you want to always have the same key. So you want to exactly measure the same path response under certain different time and also in different environment. So you don't want these path response R1 to change from measurement to measurement. And in the sense of reliability, we have basically two different types of reliability. One is in we call the short-term reliability, or in most literature is mostly called the data stability. And so this is the short-term one is the path response may change temporarily caused by environmental change, or it can be, so environmental change can be temperature, can be supply voltage, can be radiation, for example. And they're also caused by the internal fluctuations, such as white noise, flicker noise, and crosstalk, and so on. So these effects, they change the path readout, but not permanently. It's just like from this cycle to next cycle, it's different, but maybe in later couple of cycles, it comes back again. But there's also a different term. Yeah, okay, so yeah, the problem is how to improve it. And there's also another term which called the long-term reliability, which is related to device aging. So in this case, it's more severe than the previous one, typically because it can permanently change the output of a path based on these kind of known aging mechanisms, such as BTI and hub carrier. And here shows an example for you have a transistor, and you have some, if you apply a voltage stress on the transistor, you will excite the oxide traps, and it will capture the electrons or holes, and then it will indicate oxide. And then it will change the threshold voltage of your of your transistor. Sorry. So if in a certain time you have too much traps in your transistor, basically you will change the voltage, you will change the threshold voltage, and then it might change your path outcome, basically. So why we want to care about the reliability, so the good reliability is of course crucial, and how it really makes a difference is like, so in this case, as we discussed, the path-based key generation, we need to have a non-volatile memory to store the helper data to reduce to do error correction. But then it makes a doubt why we not just again to store the data in the non-volatile memory, since if we only cares about the cost, because if you still need a non-volatile memory, then you don't actually reduce the cost of the to implement this chip. So if we want to make sure that the path is more low cost than the traditional method, then we need to get rid of the non-volatile memory and the error correction. So how can we do it? So we have to make this part, the path stable, basically. And this brings us to the final part of my presentation. I'll show you a design example of how we make the path to be stable in the actual design. And so first, I will show basically some few methods nowadays used to improve the path stability, and then I will go to my own work. So here are some methods. Of course, the error correction, and it's more robust, but there are also some alternative that you can do it with more low-cost fashion. And there are three main methods. There are three main methods: temporary majority voting and masking and the burning method. So the question is, can these methods be used or combined to achieve the same robustness as you use the error correction scheme? So we'll talk about it. And so the first method of the concept of temporary majority voting is to reduce the effect of noise by taking an average. So what they do is you measure the response bits multiple times, and it will output the most occurring values. For example, here I have 3 measurements, and you have some bits are flipped, and then you will take the the which occurs the most time, and then basically in this case you have less error bits in the final output, and yeah, it can reduce the error rate. And here shows just an example of how many number of responses you need to measure to be able to reach a certain amount of error rate in the end. So, but you can see here, if you, for example, you have a puff bit which is highly unstable. For example, you have more than 40% of error rate in the beginning, then you need actually more than 100 of measurement. Then, but it can even if you have more than 100 of measurement, you cannot reduce the bits, the error rate to a sufficiently low value, so it's not so efficient. And if you need really least large number of n to reduce the error rate, you also introduce a lot of latency in your system. So so it's not also a good idea to make to use this so big number of n in this case. And the next one is the concept is to discard all the noisy bits. So the document masking. So as you see here, the example of 1 kilobit puff data, and you see there's 2 unstable bits. So basically, we mark the position of these 2 unstable bits, and so later on you will just get 1022 bits of stable puff data out. But there are also concerns of this method. So the problem is how do we identify the unstable bits? So we need to do a lot of measurement, or we need some special method to identify it, and later on so after you identify these bits, the positions, and how you store the position of these bits, then if you still need a non-volatile memory, then this brings us to the beginning of the discussion, right? So it's also may not be so good to use these methods all the time. So, and later, the last one is to exploit the time-dependent variability. As we said, this things happen for long term. So what can you do is to use the reliability issue to basically enhance your response. How it's actually done is, so for example, you have a SRAM path, which this transistor is particularly weaker than the others. So the power up pattern will be like you have VDD at the left and the 0 at the right. And in this case, you will have a BTI stress on this transistor. And actually, for a long term, this transistor will become weaker. So basically, you don't have that much difference between these 2 transistors. And how we counter this effect and make it more stable, we just don't keep the power up pattern, but we program the data to opposite way. And in this case, you will have BTI on the weak devices, and the weak device will be even weaker in a certain time. So you have to increase the difference between these 2 transistors, basically. So this method potentially works, but there's some concerns because you need to, typically for reliability to age, you need to stress it for a long time. And also for some mechanisms, you have recovery. So maybe at this point, you have a big difference, but maybe after a year, the aging is a bit reduced, then you don't have that much difference in the end. So it brings us to our own work. So we try to implement the stable path using these, we call the gate oxide breakdown mechanism. So why we choose the gate oxide breakdown? Because we know the breakdown spots in transistors are natively stable. So how it comes, so we have a transistor with an oxide, and in the oxide you have traps, and originally or you can introduce later on, but for example, we stress the transistor and it will generate more traps, and if some of the trap they are more likely to be connected, then it will be formed as so-called the percolation path, and it starts conducting more current. And later on, if this process will go, this path will grow bigger and bigger, and later on we have a breakdown. So the breakdown means these gate oxides start to conduct current. So before it's insulating, but now it's have more current which conduct through this gate oxide. And also this mechanism we call it's called time-dependent dielectric breakdown, which can be accelerated by voltage. So if we increase the stress voltage, it makes the time to generate the breakdown lower. So it can be less time consuming comparing to other other aging mechanisms. So how we use it to generate the PUF, so we have two parallel transistors which we apply a voltage stress. And for example, we have only a breakdown at the left transistor, we can get a 0 out of it. And we have the breakdown happens at the right transistor, then later on we can make it a 1. So basically we have some randomness using this mechanism. So if there's 50% of each, then we have really a good PUF implementations. And so how we exactly generate only one breakdown spot, I will go quickly in this part because it will. So basically it's, once we have a breakdown, it will start conducting current. And since the current is conducting, the voltage stress on the transistor will be lower. So once you have already a breakdown, it will not continually generate a breakdown at the other transistor. So we can make sure that we only have one breakdown spot in this cell. So basically we have only a 1 or a 0. We don't have the case with two breakdowns simultaneously. So this is how we make the circuit. So the circuit is implemented with peripheral blocks like control lines and some sense amplifier for data readout. So the sense amplifier is basically used to distinguish the current of the breakdown transistor and the non-breakdown the transistor without breakdown. So it can detect the breakdown spot is at the left or to the right. So it can give out a digital 0 and 1s. So for the measurement result, of course we care about the bit error rate of these PUF bits. So we measured multiple times and under different supply voltages. And you see for most of the cases, a higher voltage higher than 0.8 volt, we have 0% bit error rate, so it's completely stable in these cases. And also in these cases, because it's completely stable, so then we don't need helper data to do error correction. So it's what we want actually. And this right figure just wanted to show you how the bit error rate and unstable bits evolved if you increase the measurement cycle. So basically you will need enough measurement cycle to identify some of unstable bits. This reflects to what I mentioned. It's hard to identify the unstable bits. So in this case, you need more than 10,000 cycles to identify one. So it's not also shows how the dark beam masking scheme is, and it's would not work all the time. So here also shows a good data stability against temperature variation. So the bit error rate occurs only if we have really high temperature in this nominal VDD of 0.9 volt. But if we decrease the voltage, of course you see that the region of have 0 bit error rate is reduced, and if we further reduce the voltage, and it's further get worse. So it means that even if we have this stable path, then we still have to really consider which voltage range we can actually use it as a stable solution. It's inevitable because of these effects. So the last part is just to show how the PUFs are unique. So here shows the Hamming weight of each devices. So it's also need to follow the ideal binomial distribution, and it shows mostly in this region, and also it shows no bias. And for the Hamming distance, it also follows the ideal binomial distribution, so the PUF is unique. And we don't see any spatial correlations in the PUFs data, and all the sequence has passed this autocorrelation test specified here. So this summarized this design example. So based on this oxide breakdown mechanism, we can actually design a PUF which is fully stable, and for the other property like uniqueness, it's also fulfilled. So it's a good way to design a PUF. So later on, summary of this talk. So first we have introduced the silicon PUF. They are unique fingerprints in chips, and they are benefit from the process variations in silicon technology, and even more variations can be exploited in the newer technologies. And the secret key, we can use the weak PUF to generate secret keys, and we have shown the SRAM PUF as a classical example, and the helper data in most of the cases is still needed if you don't have a PUF which is stable. And we also introduced how the entity authentication can be done use SRAM path, but the Arbiter path, which is widely used, is actually not the ideal case. And the correlated challenge response pairs are prone to machine learning attacks. And uniqueness and reliability are the two main key properties for paths. And finally, we have introduced a design example which is highly stable. And this ends my talk. Thank you very much for your attention.